We're here at the example table, and in this video we're going to talk about graphing rational functions. We're going to start with a few examples, each of which illustrates an important feature of graphs of rational functions. We'll take them one at a time. So let's start with f of x equals 1 over x. I hope that you've seen this before, but even if you haven't, let's figure out what the graph is. As we go out toward positive infinity, x gets larger and larger, so 1 over x gets smaller and smaller. So we're going to shrink down towards 0, and 1 over x is going to be positive. If x is a positive number and it's close to 0, 1 over x is going to be a positive number that's very, very large. So it's going to approach positive infinity. So we get a vertical asymptote at 0. We can use the same reasoning to figure out that for negative values of x, the graph looks like this. So in particular, in this case, we have a denominator equaling 0 leading to a vertical asymptote at that x value, namely x equals 0. Let's look at an example that shows us that we have to be careful about just looking for where the denominator is 0. Let's suppose instead that f of x equals x over x. In this case, we can think of plugging in any value of x other than 0, and we get 1. 2 over 2 is 1, negative 8 over negative 8 is 1. So we get the constant function 1, except at 0. Because at 0, this is 0 over 0, which is undefined. So this graph has a hole in it. So the reason we didn't get an asymptote the way we did here is that when the denominator is 0, in this case, the numerator is also 0. So we have to pay attention for things that cancel. In this case, the x in the denominator didn't cancel with a corresponding term here. In this case, the x in the denominator does cancel with a corresponding term in the numerator. Let's look at one more example. Let's suppose that f of x equals x over x plus 1. In this case, we see that the denominator is 0 at negative 1. We don't have a corresponding x plus 1 term in the numerator, so we can be fairly certain that we have a vertical asymptote at negative 1. Now, what happens near this asymptote on this side? If we plug in a value of x that's slightly larger than negative 1, in other words, slightly to the right of negative 1, we have a negative number on the top and a positive number on the bottom, which means this ratio is going to be negative. So we're going to be approaching this asymptote like this. Now, it's going to be nice if we know where, if anywhere, this graph crosses the x-axis. If we set this equal to 0, that's the same thing as saying the numerator equal to 0, which means x is 0. So it's going to cross the x-axis right here. But what happens, so we can be reasonably sure that it goes like this, but what happens as we continue to go out toward positive infinity? Well, this plus 1 starts to matter less and less. If we plug in 100, we have 100 over 101. That's close to 1. If we plug in 1,000, that's 1,000 over 1,000 plus 1, which is even closer to 1. So this function, as x approaches positive infinity, is going to get closer and closer to 1. Now let's look at what happens on the other side. If we plug in a value slightly smaller than negative 1, we have a negative value on the top and now a negative value on the bottom also. So the result is a positive number. So we're going to come down like this. And the same reasoning that applied going in this direction toward positive infinity will apply going in this direction toward negative infinity. So we're going to approach 1 just the same. So let's put these pieces together to look at one final example. Let's suppose that f of x is x minus 1 times x plus 3 all over x minus 5 times x minus 2. So let's first try to identify where our vertical asymptotes are. We have an x minus 5 and an x minus 2 term in the denominator, neither of which cancels with anything in the numerator. So x equals 5 and x equals 2 should be vertical asymptotes. This is not to scale. This is just a rough sketch. Another good thing to know is where this graph crosses the x-axis. That's going to be given by the places where the numerator is 0. So that's going to be when x equals 1 or when x equals negative 3. So let's put a little dot here and a dot here. One more useful thing, even before we start talking about rational functions, is just knowing where the y-intercept is. So if we plug in x equals 0, we get negative 1 times 3 over negative 5 times negative 2. We could figure out what that is exactly, or as a decimal. The thing that I want to make sure I know is whether it's positive or negative. So if we plug in 0, this is negative, this is positive, this is negative, and this is negative. So we have a negative number on the top, a positive number on the bottom. So f of 0 is going to be negative. So let's just mark it right here. Now, long-term behavior in the x direction, in the positive x direction and the negative x direction. In this case, we don't have x over x like we did in the previous case, or x over x plus 1. But we do see that these two things are both quadratic polynomials. The numerator is a quadratic polynomial. The denominator is a quadratic polynomial. The behavior of the top is going to be dominated by that x squared term. Similarly, the behavior in the bottom is going to be dominated by the x squared term. So for extremely large values of x, the top is basically x squared, and the bottom is basically x squared. And likewise for extremely small values, by which I mean values very far in the negative direction on the x-axis. So, just as in our previous example, we have a horizontal asymptote at x equals 1. So we could label this even if we want this to be explicit. This is 2, and this is 5. All right, so let's start filling in the graph. Near 2, if we plug in, say, a value that's slightly smaller than 2, we get a positive number, a negative number, and a negative number. So this graph should approach from this direction, should approach this vertical asymptote up as opposed to down. So we could come down like this. We can be reasonably sure that it intersects here, and then it comes back up. We know it's going to approach this horizontal asymptote, and so it's going to do something like this. There's all sorts of other behavior that we can't really analyze now. Once you study calculus, you'll be able to make lots of other determinations about how this graph looks. Right now, we're focused mostly on how it behaves near the asymptotes and things like intercepts. How does it behave between these two things? Well, we know that it doesn't have any x-intercepts here, so it must be completely above or completely below the x-axis. Let's plug in some value, let's say 3. This is positive, this is positive, this is negative, and this is positive. So, between 2 and 5, this graph must be negative. So it must be negative, so it must do something like this. Finally, on this side of 5, if we plug in something just slightly larger than 5, this is positive, both terms in the denominator are also positive, so it's going to approach this vertical asymptote from above, and it's going to come down like this. One thing to note is that this graph crosses its horizontal asymptote. It crosses it right here. And that's okay. That doesn't violate any rules. You can't cross a vertical asymptote and still be a function, but you can cross a horizontal asymptote.